Right. Okay, we're going to make a start. Good morning, everybody. Welcome back to day two. A huge thank you to all of the speakers from yesterday. We really enjoyed the talks. I learned a lot, and I went away with that fantastic feeling that you get from a conference where your head just feels full of all sorts of new ideas. Then your brain has been used in a way that you don't normally use it. So I hope that that isn't just me, and actually that's a sort of common feeling around the room. For those of you who were staying in London, I hope you got a chance to go out and enjoy the city a bit. And we're going to make a start now. In terms of announcements, there's not a huge amount to tell you that I didn't tell you yesterday. You are welcome to enjoy the gallery today. All of the gallery spaces should be open, and it's open until 6 o'clock. So after we finish here today, if you want to have a wander around, please do. If you are tweeting about the event, I'm going to get this wrong now because there are too many letters, but it is hashtag CRTSWT22. And if you didn't get that, do have a look at the PCTU stats Twitter that I'm sure you all follow, which Rachel has been keeping up to date for us with some with that hashtag. So please do take a look at that, and please do tweet about the conference and interesting things that you find. For those of you who did have a big night out in London last night, we're going to test your brain a little bit, because in our first session, which I'm going to chair now, we have a slight switch of order. So the first person I'm going to invite up so that we can make a start is Faye Williamson, who's going to talk about sample size calculations for cluster randomized trials using assurance. So Faye, if we can welcome you up here, and I will sit down there and kind of wave frantically at you when you've got about 2 minutes left.
Yeah, I've got my phone, so I'll put a timer on. Yeah, the reason we switched the order, by the way, is just because Samuel's talk seemed to follow better after mine, so I hope that's okay.
It's not just the best people. Excellent.
No, exactly. Okay, so this work is based on a working paper, and it's joint work with Faye Williamson from the Maths, Stats and Physics department in Newcastle, who'll be talking later this afternoon. And Plourde, who is based in the Lancashire Clinical Trials Unit. So a critical task in the planning of any trial is obviously the choice of a suitable sample size. Now, in a standard sample size calculation, this requires pre-specification of parameters that are unknown at the design stage of the trial. So one particularly troublesome parameter unique to cluster randomized trials is one you'll probably all be familiar with, and that is the intra-cluster correlation coefficient, which quantifies the degree of similarity between outcomes from members of the same cluster. So typically, sample size calculations for cluster randomized trials use ICC estimates without taking its uncertainty into account, which is problematic because the sample size is very sensitive to small differences in the ICC. So a trial with a higher than expected ICC could end up being overpowered. And on the other hand, a trial with a lower than expected ICC can lead to an overpowered trial, and therefore a situation with more patients than necessary being recruited. And obviously that contributes to the problem of resource waste, etc. So therefore, robust estimation of the ICC is important. In practice, the ICC is typically based on a pilot study, but these pilot studies are often too small to provide precise and reliable estimates. So an alternative approach which is often used is to use a conservative estimate of the ICC. So if, for example, the upper confidence interval limit. However, this can lead to considerably overpowered and unnecessarily large trials. So a more reliable method is sometimes to combine the ICC estimates from multiple sources, such as previous trials, or databases listing ICC estimates. However, this raises further issues such as how to effectively combine the ICC estimates, how to adequately reflect their varying degrees of relevance to the planned trial, how to capture the uncertainty inherent in the individual ICC estimates, and also what if there are no relevant ICC estimates available. So utilising a Bayesian approach for the trial design, in which prior distributions are assigned to the unknown design parameters, such as the ICC, can offer a promising alternative to simply using the point estimate. So the reasons for this is the relative likelihood of the different parameter values can be encompassed. So it's not just using a single point estimate for the ICC, for example, it's considering the prior probability of each possible ICC value. So consequently, it allows for imprecision or uncertainty in the model parameters to be incorporated. So this is particularly useful in settings where the ICC estimates are not readily available. And also it's important to remember that there are other key design parameters which also require estimation at the design stage, such as the overall standard deviation, the treatment effect, and if the clusters are assumed to be unequal, the coefficient of variation of the cluster size. So within the Bayesian framework, uncertainty in these parameters can easily be incorporated in a similar way. So for example, in recent work by Samuel and colleagues, they assign independent prior distributions to the overall standard deviation in addition to the ICC, and then describe what is known as a hybrid approach to determine the sample size. So what I mean by a hybrid approach in this context, it just designs that utilize a Bayesian design with a widely accepted frequentist analysis method. Okay, so if we consider a two-arm parallel group CRT with normally distributed outcomes, and we're interested in testing whether there's evidence of a positive treatment effect, then for a Wald test with significance level alpha, the power can be approximated by equation 1 shown here, where so this capital C is representing the number of clusters, the n bar is just the average cluster sample size, the sigma is the overall standard deviation of the outcomes, the nu is the coefficient of variation, and the rho is our ICC. So in a standard power calculation, the sample size would then be chosen as the smallest value, which gives the required power, and it will be conditional on whatever values we've chosen for these 4 nuisance parameters, which I've highlighted in red. I'm not sure if you can see. So rather than conditioning on these fixed estimates for the parameters, which may be far from the truth, we can instead use the unconditional probability that the trial will be successful. And this quantity is often referred to as the assurance, and it can basically be thought of as a Bayesian alternative to power. So basically we would assign prior distributions to sigma, rho, and nu to capture the uncertainty in them. And in our case, we set the treatment effect equal to the minimal clinically important difference, rather than defining a prior distribution to that as well, because using the MCID is more representative of the design stage of a trial, in which the treatment effect is typically, it's already been fixed in advance by investigators. And also by doing this, it ensures that the assurance will tend to 1 as the sample size increases. So it can be used in an analogous way to traditional power, which therefore makes it more intuitive and easier to interpret. So we can then average the power function P over the uncertainty in these nuisance parameters to obtain the assurance, which takes the form of that shown in equation 2. So we end up with a probability that the treatment effect is significantly positive, conditional only on our MCID. And in practice, these values for our unknown parameters, R sub psi, will be sampled from the prior distributions using Monte Carlo simulation. Sorry, it's not moving on. There we go. Okay, so I'll now just go through a motivating example. So the motivating study for this work was called the ICONS trial, which basically is investigating the effectiveness of a systematic voiding program versus usual care on post-stroke urinary incontinence. The problem with this trial was that a robust ICC estimate was not available to inform the planning. And although a pilot study was conducted, the resulting ICC estimate was of low precision, so it couldn't be used as a reliable single source for the sample size calculation. So therefore, we used the data from the feasibility study to inform the prior distributions for sigma, rho, and nu. So the prior distributions for rho, the ICC, was based on Bayesian hierarchical modeling and expert elicitation, which combined 34 ICC estimates from 16 previously published trials and incorporated the opinions of 8 experts to determine the relevance and weights of the ICC estimates. So full details of how this prior was constructed can be found in a paper by Svetlana, which is due to appear in clinical trials soon. And this method closely follows that was proposed in Turner, Thompson, and Spiegel-Halter back in 2005. So basically, we can use MCMC samples from this hierarchical model as samples from the prior distribution for rho. So given that rho and sigma are both functions of the between cluster variance and within cluster variance, it's likely that sigma and rho can be assumed to be independent in the prior. So therefore, we defined a joint prior distribution between these parameters to account for that dependency. And this plot basically shows that joint prior distribution for rho and sigma, where it's evident that the samples of rho are positively correlated with sigma. So this slide shows the resulting power or assurance curves as functions of the required sample size per cluster for these different approaches. The red line corresponds to a power calculation based on a single point estimate from the elicited prior distribution, and the other 2 lines correspond to these hybrid versions. So basically, we see that the hybrid approach requires larger sample sizes than the power calculation when the target power or assurance is above 0.5. And this green line here includes prior information on all 3 parameters, whereas the black one is just a prior on rho. And we can see that incorporating the uncertainty on all 3, the sample size only increases very slightly. So just quickly, before I finish, this table summarizes the required sample sizes for each of the methods. The first row here corresponds to the commonly used multiple estimate method of simply taking the median of a set of ICC values. And then the other 3 methods are those just shown on the previous slide. So for the ICONS trial, relative to the approach that is often used in practice, you can see that the total sample size required is increased by 20% on average when incorporating the uncertainty on all 3 parameters. So again, yes, the sample sizes obtained by assurance are bigger than those based on power, as expected, but the cost of misspecifying any one of these parameters could be much greater than the extra sample size incurred to ensure that the uncertainty is properly accounted for in advance during the design stage. So yeah, a few concluding remarks to wrap up. We've seen that in a typical power calculation, parameters take fixed values. The ICC in particular can be challenging to estimate, and if the values used are far from the unknown true value, it could lead to trials that are substantially over or underpowered. So therefore, in this talk, we suggested a hybrid approach, which uses the Bayesian concept of assurance to determine the sample size with a wall test for the analysis. The advantages are that the assurance is a robust alternative, and it's particularly advantageous in circumstances where obtaining reliable ICC estimates are difficult. So we propose to define this prior over the standard deviation, the ICC, and coefficient of variation of the cluster size, while still utilizing the MCID. Kevin later today will show the effect of considering uncertainty also on the treatment effect, and also how this can be extended to a fully Bayesian analysis. Okay, thank you. And here's some references.
Going to try and get out to the light there. Thank you very much, Faye. That was really interesting. I now kind of want to go and try that out. So questions, well, first I'll start with, do we have any questions from our colleagues online? None at the moment. So I saw a hand up and I come running down.
Thanks, that's a very nice talk. This is probably a very naive question because I'm not a Bayesian, but what's the advantages of doing a sample size calculation this way rather than doing it by a simulation in a in a non-Bayesian way? I mean, I'd imagine I could just draw my ICC from a distribution. So
what distribution would you assign it from?
Well, I don't know. What, maybe the same prior distribution you're assigning it there. I don't know.
Yeah, so I'm not sure how those approaches would be different in that case. If you still have a prior distribution which you're assigning your.
So this is okay. So there isn't really anything Bayesian going on. It's just you're just simulating the data set and running. You're just doing a power calculation by simulation in the standard. Well, maybe I just don't understand.
Yeah,
sorry.
essentially, yeah. We're just taking those MCMC samples from a prior distribution. So yeah, we are basically using simulation here from the whatever our specified prior distributions are.
Yeah, fair enough. I'm not Bayesian. I probably just don't understand. It's probably a silly question.
Any other questions? Oh, down here. Obviously, it had to be at the end of the row. Pass that down.
Thank you. That was really interesting. I was just wondered, you seemed really focused on the idea that you really must take the minimum clinically important difference. You highlighted that as being important, and I didn't really follow. I mean, the alternative being that you happen to think that the intervention is likely to have a bigger effect than that. Are you suggesting you shouldn't use the expected intervention effect? You must use minimum clinically important difference?
So this was just a result of what is commonly done in practice. What we were advised that the minimal clinically important difference is the quantity that's often used here. So initially, when we started this work, we also assigned a prior distribution to the treatment effect to incorporate the uncertainty on that parameter too. But the argument was that, well, the MCID is typically already fixed in advance. So why wouldn't you use that? It's more reflective of practice to use that.
Okay, so it's the argument being just to sort of reflect sort of standard practice,
yeah,
rather than
basically
sort of something fundamental.
And
so,
as I said,
so
I
in principle, if you did use, you could use the same method, presumably.
Exactly,
with...
you could just as easily, incorporate a prior on the treatment effect as well. And I think Kevin maybe covers that later. Yeah, so.
Thank you. Really interesting talk. I think these hybrid approaches are very interesting. But I just wondered what you thought about there being conceptual tension between sort of claiming there's this knowledge about these parameters in the design stage and then not using any of that in the analysis stage.
Sorry, what was
Well, whether you thought it was, I mean, maybe it's a tension that could be overcome or it doesn't matter, but perhaps what you thought about kind of using a Bayesian approach when designing the trial and claiming that there's this knowledge we have about these parameters, but then when we come to analysing it, saying we must discard all this and just use the data we've collected. Do you think there's a tension there or is that okay?
Yeah, I guess so, but I guess more the purpose of this work inform sort of a robust sample size that was, took account of misspecification. But yeah, that's a good question. And again, I guess. And I guess I can. Yeah, Kevin will.
Well, that's a fantastic preview. Kevin is going to answer all the questions later. So
yeah, basically for frequentist analysis, it's make it more aligned with practice, because that's what people and regulatory agencies are typically used to. But Bayesian, Kevin does show what happens when you consider a fully Bayesian analysis as well.
Well, thank you so much, Faye. That's fantastic. Well, we'll let you get down. And obviously you've sparked a lot of interest. So come and find her during the coffee break and ask her all the questions that we didn't get time for. So next up, Samuel, if you'd like to come. Samuel's going to present to us a hybrid approach to sample size re-estimation in cluster randomized trials with a continuous outcome when there is uncertainty in the ICC. So I'm interested now because I think there's always uncertainty in the ICC.
Thank you very much, and good morning once again. So I'm presenting a study that is titled A Hybrid Approach to Sample Size Re-Estimation in Cluster Randomized Trials with Continuous Outcomes. And this is a working paper in collaboration with my supervisors, James Wasson and Michael Grilling. So I'll begin my introduction by thanking Faye because she has done a fantastic job of explaining the difficulties in obtaining precise estimates of the ICC and also talking about the statistical issues associated with such difficulty. And she has also elaborated on some approaches that could be used to mitigate this challenge in terms of sample size calculation, so I won't labor on this point. But one limitation to these approaches, especially the kind that uses a prior to express the level of uncertainty, is that their utility can highly be dependent on a choice of prior. And we know this because sometimes the prior we select often poorly reflects the data from the intended trial. So in theory, what we think is that this limitation can be addressed by sample size re-estimation, which is an adaptive design that uses a proportion of the trial data to estimate these nuisance parameters. And when I say nuisance parameters in this context, it will be the ICC. And now the estimate from the interim ICC will be used to determine the final sample size. Given the background that studies that have conducted sample size re-estimation in the context of CRT has been frequentist in nature, these point estimates from the studies actually perform poorly in practice as they ignore uncertainty in the interim estimate of the ICC. Therefore, you realize that there is large variability in the re-estimated required sample size. So it is against this background that we seek to develop a hybrid approach to sample size re-estimation that allows for uncertainty in the ICC. To motivate this study, our example parameters were extracted from a study by Hancock et al., which is a study that sought to reduce adolescent sedentary behavior by improving physical activity in schools. And the study assumed no ICC at the design stage of the trial. They used an internal pilot of 25 clusters with an average cluster size of 17 to estimate the ICC at the interim analysis. Additionally, the study was powered at 80% to detect a difference of 0.3 for a standard deviation of 1.3 and an alpha level of 0.025. So I'll begin the methods by just describing a general algorithm in performing sample size re-estimation. And the first step is to have some initial number of clusters, and you can determine this initial number of clusters with the assumed design parameters at the design stage of the trial, or you can say take some number of clusters that you feel is reasonable to begin with that you would use to extract this estimate from at the interim analysis. So to follow the motivation example, we'll be using 26 clusters for equal allocation between the arms, since they use 25 clusters for the pilot study. And the next step will be to re-estimate the sample size or determine the final sample size based on the estimate of the ICC you got from the interim analysis and the other design parameters that were listed in the earlier slides. And then the next step will be to find the remaining number of clusters. And this is by finding the difference between the final sample size or the re-estimated sample size and the initial sample size you used at the beginning of the trial. And after this step, you are faced with two rules of thumb. And the first one is if your remaining number of clusters is less or equal to 0, then your interim analysis becomes your final analysis. But then if your remaining number of clusters is greater than 0, then you combine the outcomes from the initial number of clusters and then the remaining clusters into one data set. And then you fit either a linear mixed model, a GEE, or whichever model you find more comfortable to the data. And I must add that this framework works both ways for the hybrid and the frequentist. The only difference is how sample size is determined in these two frameworks. So the sample size determination in the frequentist framework, as we are all aware, basically calculates the sample size for an individual randomized trial and then makes consideration for the clustering by multiplying it by a design effect. And here I have highlighted the ICC in red, which is a point estimate in this particular formula like Faye mentioned, and it ignores uncertainty. But in the hybrid framework, there are quantities that are used to determine sample size calculation. One of them is the expected power. And what the expected power basically does is it takes on the frequentist power here, but makes consideration for uncertainty by placing a prior on the ICC. And this prior on the ICC is not a prior in the full Bayesian sense, which is expected to be updated to form a posterior. But then it is just categorizing likely values of the ICC for the sample size determination. And because we will be doing sample size re-estimation, we are hoping to have two priors for the hybrid approach, where the initial prior will be our initial guess. And after observing some data, this prior will be updated to form a posterior. And that posterior will now be our new prior for the final sample size determination. I hope I didn't confuse you. So moving on to finding this posterior for the ICC, there is a nice paper by Okuamin who proposes a normal approximation for the variance of the ICC using Fisher's methods. And then it is given in the formula where the ICC is normally distributed to the mean row, and then the variance which is given in that formula, long formula, which I don't want to go through because of time. And so adopting this as a likelihood, we'll be able to determine the posterior for the ICC that will be used at the interim analysis to determine the final sample size. And if you look at this likelihood, it's a bit complex and it is not actually in closed form. Therefore, we use the RJAX to sample from the posterior to form the ICC, since we couldn't have any closed form distribution to use as the posterior for the ICC. Our next important question to answer is the choice of prior. And as we know that the ICC ranges between 0 and 1, it means that any distribution that has 0 and 1 as a support can be used as a prior distribution for the ICC. So a beta distribution could be a good candidate prior for the ICC. But for this study, we use a truncated normal prior, which is truncated on 0 and 1. And we denote the prior mean by M1 and the prior variance by S1 squared. And here is just a plot of the various mean and standard deviations we use for the initial plot of the prior. And what we wanted to see is how a small prior mean, a moderate prior mean, and a large prior mean kind of impact this sample size re-estimation procedure. And in the frequentist framework, these values would be point estimates in their calculation. And to express the level of uncertainty on the hybrid framework, we would look at how a small variance and then a large variance also impacts the final sample size and the interim estimate of the ICC. I don't know. I'm so sorry, but the first slide, okay, I know what is there. It's unfortunate. I'm very sorry. I apologize for this. But the first slide actually shows that on the average, both frameworks, that is the frequentist and the hybrid, perform well in terms of the interim estimate of the ICC and then the final estimate of the ICC. There is no significant difference in the interim estimate of the ICC on the average for the frequentist and that of the hybrid framework. The only difference you see small is that when you increase the variance on the prior for the hybrid framework, the final sample size gets to move up a bit, as Faye said. And also in terms of the type 1 error rate, the hybrid framework looks more controlled when the variance on the ICC is very small than in the frequentist framework. But apart from that, there is no difference in the estimates of the interim ICC and then the final sample size on the average. That is what table 1 was supposed to show. Yeah. But to the main question why we decided to do this sample size re-estimation was to look at the variability within the sample sizes in terms of the frequencies and the hybrid framework. And from the violin plot, you could notice that the variability within the hybrid framework is more controlled as a consequence of the Bayesian approach being more precise and its ability to see data and update the prior and now give you a more precise posterior for the final sample size determination. And that is a property that the frequencies framework doesn't have. That is why you see the variability within the frequencies framework being large. And what we want to do is to have methods that has high precision, like we see in the Bayesian framework, and not have high variability. So it makes the frequencies framework of sample size re-estimation appealing on the average. But then if you look at it in terms of data points, the variance is very large for the frequencies compared to the hybrid framework. So in conclusion, I just have these two take-home points that on the average, sample size re-estimation for both framework perform very well, and it is better than adopting a prior or even having an educated guess. But then if you look at the data set, you look at the variability within the hybrid framework is more controlled than that of the frequencies framework, which makes it more appealing. And because this is a working paper, I am happy to take more suggestions on other areas to look and investigate and improve upon the final draft of the paper. Thank you very much for your attention.
So much, Samuel, and true professionalism there, being able to talk to a bright crowd of knowledge and still give us an idea of what was going on. So well done, brace under pressure there. Do we have any questions from online? No, Garuma is saying. So from the room, I can already see one.
Thank you so much for this work. Also to Faye as well, to say thank you. Can you shed any light as to whether this approach would be applicable in the setting where you're not going to change the number of clusters, but would ideally like to maybe not have to collect as much data in each cluster? I believe I think you're exclusively presented the setting where it's about changing the number of adding additional clusters. Yeah, thank you.
That's a good point, and that is something we'll be considering. But the initial draft and the initial concept is to add on clusters. That is if at the interim analysis you find out you need more than you took initially. But then we are also looking at cases where you just have to update the sample size per cluster and not to just add clusters like you want to.
Yeah, just to say that would be really great to add to your work. Yes. You're asking for suggestions.
Can I second that? That was my question too.
Thanks for the presentation. I don't have a question, but just a comment. And a colleague of mine has written his PhD thesis about prior elicitation. I guess only part of the thesis, but he publishes in the social science literature, so you're probably not aware of that. His name is Duco Veen, V-E-E-N. So you may want to have a look at his website. He also has a shiny app about prior elicitation. So again, it's Duco Veen in Dutch, V-E-E-N. So you may want to have a look at it.
Thank you very much.
Brilliant.
Thanks very much. Really nice talk. So my question's about linking with Faye's. I think I didn't quite catch when you said, so with Faye's, you got the expert prize, you elicit that, and then so you determine your sample size. In yours, when you update the ICC, you're not using that initial prior that Faye's method would have used. Are you using that as your prior that's then updated, or are you using a different prior in yours?
Yeah, so that's a good question. So what you do is that you have an initial prior, and that gives you an initial sample size. But then this prior gets updated, in the middle of the trial, and now becomes a posterior. And now that posterior becomes your new prior. Sure. So you have two different priors, one initial and then one other.
Your initial prior is different to Faye's initial prior.
Yes.
And why so?
So here the reason for this is that we are assuming that sometimes people do not even know what to assume as an estimate for the ICC. So it could be any flat prior or any prior that has no information, like Bayesian elicitation does, and that we are expecting that at the interim, having observed some data, no matter how wrong the prior was, it will be updated, and then that will give you the precision you need for your final sample size.
And just check just so quickly. When you update the ICC, that's separated by treatment arm. That's fully unblinded, not pulled across treatment arms. Is that right?
Yeah, that's fully unblinded, but
Yeah.
we are looking at both blinded and unblinded models to see how both approaches work.
Okay, good. Thanks.
I'll just check with Garima. Do we have any other comments from online? No, any more in the room? No, well, in that case, I will thank both of our speakers. You've given me a lot to think on. I usually just go with the frequentist plump for a number and hope for the best. So that's been really interesting to hear. So thank you all very much. And it's coffee time. So you can ask them more questions up there.
So I'm Andrew Forbes from Monash Uni, Melbourne, Australia. It's my pleasure to be chairing this next session. So we've got 2 rapid fire talks, and then we've got three talks, one of which is moving to online, and I'll talk about that in a moment. But first up, we've got our 2 rapid fire talks, both on step wedge trials, both from Yale University and in sort of related areas. And so without further ado, I think we'll go to our first one, which is Dr. Mary Ryan from Yale, power calculations for cross-sectional step wedge cluster randomized trials with a time to event endpoint. So let's hope this works well.
Can everyone see that?
Mary, over to you whenever you're ready.
Excellent. I don't think I can turn on my video, so this is what y'all will have to have for now. So thank you very much. My name is Mary Ryan. I'm a postdoctoral associate at Yale, and I'm going to be presenting some work I've been doing with Drs. Sesserman and Van Lee on power calculations for cross-sectional step wedge trials with time to event endpoints. So I think, as we have seen over the last couple of days, step wedge trials are commonly designed for continuous binary or count outcomes. But there are increasing numbers of step wedge trials that have been proposed with time to event outcomes, although there's not a lot of general methodology that's been published and really no marginal model methodology. And so one example of some of these survival step wedge trials is this pediatric ventilator liberation study, where they were looking at time to successful liberation from the ventilator. And it was a cross-sectional study where there was right censoring at period end. And what was really interesting about this study is that it specifically cited a lack of step wedge survival methodology as an issue in their study protocol, particularly about powering the study. So in that particular study, they used continuous timer duration as the response when they were doing their power calculations, but others might use a binary outcome framework at the design stage and then maybe go on to analyze as time to event or continue with the binary analysis. But as we can probably imagine, analyzing survival endpoints as binary is going to result in a power loss. And in simulations, we've shown that in small sample sizes, this power loss can be quite large, up to 26%. So today, I'm going to talk about how we can find a marginal analysis method to be able to analyze step wedge trials with time to event endpoints. We're going to establish analysis validity through simulations of operating characteristics, and then we're going to derive some accurate sample size and power formulas to be able to plan for such a study. And I'm going to propose that we use a stratified Cox model for this purpose, where we are going to have period-specific baseline hazard functions, so we don't have to use fixed effects for the periods, which means that we aren't going to have a strong parametric assumption about the period or time effect. And there's no need to estimate a large number of extra coefficients, particularly when we were thinking of that ventilator study where they had 22 time points. That would be quite a lot of extra coefficients to estimate. So this kind of saves us some efficiency there. And there are 2 kind of paradigms that we can think of for testing for our treatment effect with this stratified Cox model that are going to address kind of the small cluster sizes that we usually see in step wedge trials. First would be a t-testing paradigm, although it's kind of known that t-tests are too liberal on their own, so we can apply some finite sample corrections that'll better control the type 1 error rate that have been shown in cluster randomized trials or non-survival stepwise trials. Or we can use a robust score testing paradigm where the type 1 error rate is usually fairly well controlled when we have a small number of clusters because we don't need to estimate the alternative distribution, but this can be a little bit conservative. So what we're going to do is we're going to modify some existing finite sample bias corrections in the walled and robust score settings. Our kind of baseline is going to be the robust sandwich estimator. And then we're going to compare the Faye and Gravaud, the Cowerman and Carroll, and the Menkel and Derone finite sample variance corrections for the walled test, and then a modified robust score test, just weighting the score variance by n-1 over n to make it a little less conservative. So we want to see how the walled t-test and the robust score testing paradigms compare in simulations to figure out the best way to conduct difference with our stratified Cox model. We performed a bunch of simulations under a couple of different scenarios, including varying periods and clusters and cluster sizes. We also looked at a couple of different settings for within and between period dependencies. We're just going to look at one setting here, and we used a Kendall's tau to kind of calibrate those. Looking at type 1 error rates, our kind of first row here are simulations under the walled t-test, and the bottom row here are simulations under the robust score test. We see that generally both paradigms are able to control type 1 error rate pretty well until we get really small numbers of clusters around 10, where we see that the walled t-test does have some inflated type 1 error rates, even with our bias corrections, whereas the robust score test is generally able to keep the type 1 error rate around the nominal 0.05 level. Moving on to empirical power, though, the different colors of points here denote different levels of treatment effects. And I have a reference line here at 90% power. We see that the walled t-test and the robust score paradigms have comparable empirical power, although when we have really small numbers of clusters, cluster sizes, numbers of periods, we do see that the robust score test tends to be a little bit more empirically powerful than the walled test, although this tends to kind of converge as we increase our numbers of clusters. Just kind of restating what I just said. So now that we've established the validity of this analysis testing framework, we need to be able to plan for and power our stepwise trial, which means that we need an explicit variance expression for our treatment effect. And as we've kind of seen a little bit before in this conference, we can use a robust sandwich variance estimator where the inverse A is going to be the variance under a working correlation assumption. And then the B is going to be the variance of our score statistic. And in stepwise trials, this really amounts to taking the total marginal variance plus the total within cluster period between subject covariance and the total within cluster between period between subject covariance. Because this is a cross-sectional, we don't have to worry about the within subject covariance so much. We have kind of derived explicit expressions for these, but they're a little bit messy. And it's a lot easier to think of this in terms of correlation or ICCs. So if we redefine our marginal variance as sigma, and we note that this is the general form of our covariance expression, we can define a within period ICC reparameterized to the martingale scale, and a between period ICC that takes the covariance for the between period clusters. And we can express the B part of our sandwich variance as this form down here, which is much cleaner. And if we plug it into our variance expression, we see that it takes on a very similar form to continuous GEE variance expressions, so other variance expressions that we already know and love. And just noting that the variance of the robust score statistic would kind of be a modified version of the B portion of the sandwich variance. So now that we have our explicit variance expressions, we can plug these into general classic power formula for the walled t-test and the robust score test, and see how well these power predictions compare to the empirical power we got in our simulations. So this is looking at the difference between empirical power and design power, where positive would mean that we under predicted power at the design stage. And we can see that both the T paradigm and the score paradigm both tend to underpower a little bit. But as we kind of increase our cluster size, the robust score paradigm tends to get more accurate faster than the T paradigm. And then at the lower levels of clusters, it does tend to be a little bit more accurate. So we have learned that a stratified Cox framework can flexibly analyze step wedge trials with censored time to event endpoints and account for time confounding. The step wedge robust sandwich variance expression is going to mimic a form that we have already seen in continuous GEEs, but we just need to be able to reparameterize ICCs to the martingale scale. We have shown that both walled and robust score testing paradigms can maintain type 1 error rates even when we have finite samples, although the robust score is going to be more accurate in predicting power, and it's going to be slightly more empirically powerful than the walled test, particularly in really small finite sample settings. This is my funding information and my references, and thank you all for listening.
Thank you so much, Mary. Do we have any questions online? Sorry. Oh, you don't have any online. What about in the room? Yeah, I have one myself. Concerns independence, independence work and correlation, which we had some vigorous discussion about yesterday. So in the context here, would it be possible there could be far greater efficiency if you used like a shared frailty Cox model here? So you'd be moving away from a working independence assumption to a working exchangeable assumption, and that could make use of both sort of vertical and horizontal comparisons in the step wedge design. Whereas my hunch here with sort of your stratified Cox model with periods is really doing like vertical comparisons there. So you may be missing out on some greater efficiency. I don't know if that's a very easy, very difficult question, but be interested about, I guess, other types of modeling of the working correlation, particularly shared frailty.
I think it's possible it might be slightly more efficient, but I think, and correct me if I'm wrong, with frailty-based survival models, you run into the issue of violating the proportional hazards assumption. So the marginal framework kind of works to avoid that a bit.
Oh, sorry, that's a question. That's a question for me. I'm not sure of the answer for that. That could well that could well be the case. It'd be worth looking at and seeing. Yes, I know there are all sorts of issues. You know, you bring in frailty, you bring in other sorts of issues to be dealing with as well. But thanks. Any questions from the room? Nope. Okay, let's thank Mary again. Thank you so much, Mary. Oh, just a final question, Mary. Is there a preprint of the paper up yet? Are you at that stage? What stage are you at?
We are at the first draft stage, so a paper exists, but it's not ready to be released on arXiv quite yet. So hopefully, or after the holidays, that's where we're going to be.
Okay, great. Yeah, look forward to that in due course. Right. Okay, next up, also from Yale University, is Dr. Kendra Plourde, who's going to be talking about power analysis for step wedge cluster randomized trials with continuous co-primary endpoints. So Kendra, are you up and ready?
Yeah, can you hear me?
Yes, thank you. That's great.
Perfect. And I hope you can see my slides.
We can see a background.
Oh, okay. Let me try.
Yeah, I'll let you know once we can see it. Probably loading. Yeah, loading now.
Oh, it's loading now. I just stopped the share since it didn't seem to be working. Let me try again. Let me try sharing a different screen. Let's see if it works better.
Yes, that's great. Perfect.
All right, great. I'm glad I checked so that you didn't just see a bunch of flowers the entire time I'm talking. So
That wouldn't be
thank
dissimilar
you.
to an earlier slide.
Well, thank
Okay,
you
thanks
for
very much,
having me.
Kendra. Please go
Oh,
ahead.
thank you. All right, I'll go ahead. Thank you for having me. Today, I'll be talking about the work I've been doing with my mentors, Dr. Fanley and Dr. Monica Talliard. Again, on power analysis for stepped wedge trials with continuous co-primary endpoints. So as Mary mentioned, and I have a very similar figure for stepped wedge, we're working under the stepped wedge paradigm. And so the motivation for this work under co-primary outcomes comes from a real stepped wedge cluster randomized trial. They did not have co-primary outcomes, actually. They had just a binary primary outcome, but they had many secondary outcomes of interest. And two of those outcomes of interest were these subscales of the Nottingham Health Profile. They're two quality of life measures. And looking at these quality of life measures, we knew that they were probably highly correlated with one another. So our question was, if we were to rerun this study, which I'll refer to as the IP-SDM study, how would we design this study if those two quality of life measures were our primary outcomes of interest? And so the whole idea of co-primary outcomes under cluster randomized trials is not new. There is work that's already been done, especially with power and sample size and analyzing these types of trials. Here I show the current methodology under the multivariate linear mixed model framework, where we have X sub I J is an indicator variable for the intervention. And so delta, here's our intervention, well, it's a vector of endpoint specific intervention effects. And so we are simultaneously estimating an intervention effect for each of our L outcomes. And then this B sub I is a vector of random cluster effects, which is assumed to follow a multivariate normal distribution. And so from the talks yesterday, where we're talking about correlation structures, under a linear mixed effects model, having only a random cluster effect corresponds to just a exchangeable correlation structure, which we know is not enough for stepped wedge. We really want to at least differentiate the within and between period correlations to avoid an underpowered trial. And so this means that to form power or to calculate power and sample size under a stepped wedge with co-primary endpoints, we need to run a lot of simulation studies, and you'll see how extensive it can really get and computationally intensive, because we have a lot of different ICCs we want to consider under this framework. So our goal was to generate appropriate and efficient procedures for designing this type of trial. And so here I have our proposed model, where in blue is what we've added to the current methodology. So first we have beta J, which is a vector of fixed time effects, because we know that time is a potential confounder in stepped wedge trials. And then we add this vector of random cluster by period effects, this S sub ij. And so by adding this additional vector of random effects, we now are differentiating the within and between period correlations. And we let this vector of random cluster by period effects again to follow a multivariate normal distribution to be under the multivariate framework. And so our model gives us the following ICCs. We have within period endpoint specific ICCs. Oops, did not need to go on to the next slide. We have within period between endpoint ICCs. Oh, I should stay up here, I guess. Between period endpoint specific ICCs, between period between endpoint ICCs. And since we are taking taking more than one measure on each subject, we have an inter-subject ICC. So you can see we have a lot of different ICCs. We don't have very good estimates of ICCs. So we want to look at a lot of different ICCs when we're generating power and sample size. And so you can imagine how computationally intensive this could get. And so we want to generate power and sample size, but we need to have a hypothesis test of interest. And so under a co-primary framework, we decided to focus on the intersection union test, which I'll refer to as the IU test. And this test requires that every single intervention effect has to have a statistically significant positive effect on the outcome in order to reject the null hypothesis. And so under this hypothesis test, we can form our power calculation. Here we can write it in terms of a multivariate integral of this function f, which is characterized by the individual intervention effects, as well as their variances and covariances. And so when we're generating power, we commonly have an intervention effect of interest, but now we need to focus on how do we get estimates of these variance and covariances. So to do that, we use the feasible generalized least squares formula here, shown with ZI is the design matrix, and VI is a covariance matrix of the L outcomes. And so we can write this covariance matrix in terms of our random effect covariance matrices shown at the bottom of the slide. And so we can plug in this formula. We have the design matrix. We can do block matrix inversion, and this gives us a expression for that covariance matrix of the intervention effects shown here, which is in terms of our covariance matrices for our random effects and our error. And also it depends on the U, V, and W, which are just typical design constants. And then, of course, individual variance and covariance components are not very helpful when we're trying to generate power or sample size. So we rewrote this in terms of the ICCs. And so then we wanted to validate our power methodology. Here we considered just 2 co-primary outcomes similar to our motivating study. And we varied the total number of clusters, number of periods, cluster period sizes, as well as all of the different ICCs. And what we found is that the empirical and predicted power shown here at the end in blue were always in agreement within about 3% of one another. So we found that our power methodology was well validated. And so then we went back to the IPSDM study and we said, okay, now we can answer our question. How would we have designed this study if those quality of life measures were our co-primary outcomes? So we were lucky enough to get data from the IPSDM investigators. So we ran our model to get the estimates of each of the variance and covariance components, translated those to ICCs, as you'll see here on the slide. And then we assumed we had a clinically relevant effect size for each of the intervention effects. And then assuming 5 time periods, which is the same number of time periods in the original study, we estimated that we would need 16 clusters with 12 subjects per cluster period to achieve 86.3% power. And that's, again, based on the intersection union test. And so, of course, because of time, I can't go into everything we've done. We looked at a lot of different simplifications and also extensions to closed cohort designs. Hopefully this work will be available in the coming months in statistics and medicine. And so I want to thank my mentors, Dr. Fan Lee at Yale and Dr. Monica Talliard at the Ottawa Hospital Research Institute for all their help with this work. And also just mention that this was funded through the NIA Impact Laboratory. And I have some references, and thank you. Happy to take questions.
Thanks very much, Kendra. Yeah, thanks. Interesting journey through the forest of ICCs there. As the work gets complex, we get more and more of these. Do we have questions online? No questions online. Questions from the room? Because I have a question. I mean, we're starting to deal with co-primary endpoints. I guess this is not a cluster trials specific question, Kendra, just more generally about co-primary endpoints and just your use of the intersection union principle there to control the the type 1 error rate. So that requires rejection. I mean,
Yeah, I can go back to the slide.
yeah, no, that requires both. It's a joint null. So both rejected at alpha level. Is that right?
Yes. Yeah. And throughout this work, we assumed an alpha level of 0.05. Yeah.
Yeah. So my question is about just the discussions with investigators about doing this. So that sort of defines success of the trial. You need to see success on both endpoints. It is not a cluster trials question at all. Whether in your particular example, the investigators would be able to say, conclude, well, the intervention was effective on one of the co-primary endpoints, but not the other. And then how you then interpret the trial when everything's been designed to say it's a success, which is sort of targeted towards the pharma industry towards the next stage of marketing or drug approval, etc.
Yes, exactly. Yeah, and I just want to mention, we did actually look at that scenario where, especially when you only have 2 co-primary endpoints, it could be feasible that, you know, success is defined by just one of them being significantly different from 0 even. We refer to that as the omnibus test, and we did include that in our paper, but of course for time, I couldn't go into depth, but it would be a more powerful test.
Yeah.
You only need one of them. Yeah.
Yeah. And the other alternative, just simple bond-for-only splitting of alpha, would be terribly conservative with the endpoints being so correlated to. Yeah. Yes.
And anyway, you lose out on efficiency as well, because if they're highly correlated, you kind of get a gain in power in that sense. So we didn't look at Bonferroni, but I would assume it's not only conservative, but it would be not taking into account that correlation between outcomes could also additionally hurt you.
Sure. Yeah. Okay. All right. Thanks very much, Kendra. A lot of work compressed into 10 brief minutes. So thanks so much.
Thank you, everyone.
Okay. Our next speaker is Lee Kennedy-Shaffer from Vassar College in the USA. Now, you might know Lee was here yesterday, but unfortunately he's not feeling well today. So he's going to be delivering his presentation live from his hotel room, I believe. Probably camera off. Oh, there you go. So Lee, I hope are you there, Lee?
Yes.
Yes. So sorry to hear you're not well, and thanks for still agreeing to give your presentation. This must be under somewhat adverse circumstances you're in, but thanks so much, and please go ahead when ready.
Well, thank you very much, and thank you.
Oh, Lee, yes, so Lee's title is, well, you can see it, Quasi-Experiments and Step Wedge Designs Connecting Disciplines, and I think look forward to seeing this because there's a lot of work about sort of analogous type step wedge designs in the quasi-experimental literature. So yes, so thanks, Lee, go ahead.
Thank you very much, and thank you to everyone for accommodating this shift today. So indeed, yes, I will be talking about stepped wedge designs specifically, and quasi-experiments, especially difference and differences. And I imagine many folks are familiar with difference and differences at some level. This is a quasi-experimental method that's commonly used in economics. And the basic idea, in the simplest case, you have 2 units, usually clusters, measured in 2 time points, and one of them is treated between those 2 time points. One of them is untreated at both time points. And you use the path of that untreated cluster as the counterfactual path for the treated cluster. So to remove that time confounding by using that unit that's untreated in both time periods. And so the key assumption here is that the 2 would have parallel trends in the absence of intervention. And that's the key to causal identifiability in the difference and differences case when we don't have randomization. Now, recently, there has been a flurry of activity in the econometrics literature, specifically focused on more complex difference in differences cases with staggered treatment adoption. So now the setting where you have multiple time points, multiple clusters, and some of them cross over from control to intervention at different times throughout the observation period. And if this is starting to sound a little familiar to those of you who work in stepped wedge, it is essentially a non-randomized stepped wedge design, but trying to exploit some natural variability in the time at which units cross over. It's often less evenly spaced than stepped wedges, again, because you don't have control over those time points. And the challenges of this design, again, you need parallel trends assumption, but when you have this staggered treatment adoption, it brings with it other challenges, including finding an appropriate causal estimand, which clusters at which time points for which duration of time on treatment are you interested in measuring the causal effect. And a very important paper recently by Andrew Goodman-Bacon found that the prominent designs that are used to analyze this, this type of data can give you bias when there is treatment heterogeneity. So a lot of the recent literature has been reconsidering these estimands and examining that bias that arises. And specifically, this bias arises in what's called the two-way fixed effects analysis method. And this is a method that's very, very similar to the Hussey and Hughes method that's commonly used in the stepped wedge design, except that it uses only fixed effects instead of a random effect for clusters. And this bias arises when there is treatment heterogeneity because that analysis method essentially uses early crossing over clusters as a control for later crossing over clusters. It inherently in the model assumes that the treatment effect does not change over time or over time since the intervention began. And so to address this issue, there's been a reconsideration of a lot of economics results and a lot of methodological work to propose new estimators and to understand the properties of these estimators and settings where they might be, where different estimators might be more useful. And I will say some of the economics literature is very challenging for me, at least, to read as a non-economist. I think if you're interested in one really nice overview of a lot of these methods and challenges, I would highly recommend this paper by Andrew Baker and colleagues. So what does this have to do with stepped wedge trials, with cluster randomized trials, which is why we're all here? Well, this issue that's been raised of the treatment effect heterogeneity causing bias can actually appear in the stepped wedge setting as well, right? This is not an issue that is just a result of the confounding from the non-randomized nature of difference in differences. And in particular, you can actually use this Goodman-Bacon decomposition method to tease out the different contrasts, the different causal contrasts that contribute to the overall effect estimator. And those will be a combination of groups, clusters that are treated earlier being compared to clusters that are on control, and clusters that are treated later being compared to clusters that were already treated earlier. And those contrasts can be negative if the treatment effect increases over time. So the danger is you can actually get an overall treatment effect estimate that is outside of the range of the individual treatment effects in each cluster period. Now, that extreme case is only likely to happen if you have pretty strong time trends in the treatment effect heterogeneity. But even without those strong trends, it's still unclear exactly what causal estimand is being targeted in some cases by the overall estimate. So there are some methods to fix this. Lindner and McConnell recently published an article that brings over one of the methods proposed in the difference in differences literature to the stepped wedge case. And this approach, just to give a brief idea of it in the interest of time, it really includes a lot of individual treatment effects. So these theta sub JLs here allow that treatment effect to be different for different clusters and different amounts of time since their intervention began. And so that can address this problem in some settings. Another approach is more non-parametric, and this is kind of a generalization of the non-parametric within period method that Jennifer Thompson and her colleagues have proposed, and a crossover method that I developed with some colleagues a few years back. And Fan Li and his colleagues actually noted the specific connection between this crossover method and the difference in differences literature recently. And the idea is, well, instead of letting the model determine the weighted average of all of these individual contrasts, we can do all of these contrasts ourselves. We can make all of those possible 2x2 difference in differences comparisons, those simple comparisons where you just have 2 clusters and 2 time periods, and use that to get a treatment effect estimate for each of the intervened upon cluster periods. And then we'll have a whole array of these treatment effects, and we can look at them individually or combine them into some overall effect with an explicit weighting scheme. And one challenge, and this is still early work on this estimator, but one challenge is thinking about what are the weightings, what are the overall averages that might actually be most useful in certain settings. One nice thing about this approach is that it can actually be shown to fit within some of the theoretical frameworks for stepped wedge estimators that have been proposed. So it can fit within that design framework that's been proposed, and you can actually force the weights on all the rows and columns to equal 0. And if you believe in the centrosymmetry of the underlying data generating process, you can actually enforce that centrosymmetry on the estimator as well. So this is a general approach, but that can be made to fit within some of these frameworks depending on our beliefs about the underlying process. So that's one value that we can draw from this difference in differences literature is developing new estimators that might be useful. There are also other things that I think we can gain from this literature, this explicit consideration of estimands that's been going on in the clinical trials side, specifically as well as we heard yesterday. But there might be things that we can learn from the econometric side as well. In addition, it actually opens up a huge new literature base. So for thinking about the assumptions we're willing to make about treatment effects and time effects, for trying to get data and realistic simulations for different outcomes and interventions, we can now actually tap into all of the published difference in differences literature, and we might be able to find useful settings and useful information there that will apply in the stepped wedge case as well. And for more complex designs or cases where the randomization might be broken by dropout or not following the treatment regimen, there might be useful information there from the difference in differences literature as well. And I think the work that we're all doing on cluster randomized and stepped wedge trials can inform a lot of this difference in differences work as well. In particular, issues of variance, power, and sample size are much, much better developed in the clinical trials side than on the observational study side, as well as some of these theoretical frameworks about estimators that exist. And so bringing those to the attention of the econometrics researchers and that field can help improve their work as well. And this is just, I think, one specific setting where there might be crossover potential between these disciplines. More generally, what are known as panel data methods in the economic literature and what we're all doing with cluster randomized trials. I think those two fields share a lot of opportunities and challenges, and there might be ways to both broaden the impact of our work and improve our work by building on what's been done in that setting as well. Thank you.
Thanks very much, Lee. Very interesting linkage between econometrics and sort of biostatistics area. Yeah, there really is so much overlap that things are reinvented in one of the other disciplines, and each has got so much to learn from the other. Any questions online? No, any questions in the room? Yes, Richard, go ahead. Oh, I do too, yes. Thank you.
Thanks, Lee. I enjoyed that talk. I'm very interested in this. I'm a bit wary of differences in analyses in randomized studies like step wedge trials. Andrew might explain this better than I can, but in a step wedge trial, for example, the generalized least squares estimator is kind of combining differences estimates of the treatment effect with estimates just by comparing intervention and control concurrently. And that gives you a very kind of efficient combination of within and between. Have you come across this? Does this chime with what you're thinking?
Yes. I think certainly any of these more non-parametric approaches will not have that same efficiency as generalized least squares or mixed effects model approaches. So I think there is a really big risk of a bias variance trade-off here, or maybe even I would think of it as almost an interpretability versus variance trade-off, which is, are you going to have a method that finds the most efficient weightings, or are you very interested in a specific interpretable a specific interpretation of the estimand, and so want to choose the weightings yourself, but that will certainly cost you in efficiency. And so I think figuring out which settings might fall into those two camps is really important for determining which side of that trade-off we want to be on in each setting.
Okay, thank you.
Okay, thank you so much, Lee, and hope you feel better soon.
Thank you very much.
Okay, let's move on. We're a little behind time, everyone, because we had some online technical issues, but I don't want to squeeze the talks of those who are going to be here in person. So we'll, with your permission, we'll keep the allocated time slots, the allocated 15-minute slots for all the speakers. So next up is, yes, coincidentally, a nice segue from Lee, one of his earlier comments about difference in differences bias when there's delayed effects of treatment. And our next speaker is Lara Maliev from Harvard, talking about assessing exposure time treatment effect heterogeneity in step wedge trials. Okay. So I'll give you a little 2-minute warning.
Okay,
We've done.
that's right.
Yeah, that's right. Okay. Now, hoping. You go with the Mac? Oh, good.
Oh, cool. That's easy. Okay, great. So thanks for the introduction. This is joint work with Fan Lee at Yale, Sebastian Hanous at Harvard Chan, and Ree Wong at Harvard Pilgrim. So thank you to them for their collaboration. So I think sorry, I have the wrong order. So first I'm going to go into some background on kind of time treatment, exposure time treatment heterogeneity and why it's important to account for it in step wedge trials. Some existing methodology and our proposed methodology for accounting for exposure time treatment effect heterogeneity, a data example, and then a and then a simulation study to assess our methods, and then conclude with the discussion. So I think we all know what a step wedge trial is by now, but I just wanted to introduce some notation. So we're going to use capital K to be the number of clusters observed in the trial, capital T, the time period, the maximum time period observed, and capital E to denote the maximum exposure time period observed. So we kind of have this third axis here of exposure time. And so in this simple step wedge schematic, you would have 4 clusters. So K equals 4. 5 time periods, T equals 5, and the maximum exposure time observed was in cluster 1, and that would be E equals 4. So we would say E equals 4 for the entire trial. In step wedge designs, the study design itself induces an association between time and the intervention effect. So we often adjust for calendar time as a confounder in standard models. And the time since intervention was introduced, which we call here exposure time, may affect outcomes cumulatively. So that's really the heterogeneity that we're focusing on in our work. So an example of this is when assessing the effect of exercise on clinical depression, the full effect may take weeks or months to reach. So there's a lot of different design or analysis methods for step wedge trials. So this work is focused on primarily generalized linear mixed models. And I tried to avoid putting too much notation here, but in all the models we considered, we're using a fixed background calendar time effect to adjust for calendar time and a random intercept indicating cluster membership. And what we're varying is the formulation of exposure time. So I'll first go through 2 commonly used models and kind of make explicit their implicit assumptions on exposure time, and then talk about our proposed methodology. So in this step wedge design schematic, we again have 4 clusters and 5 time periods, and the 0 indicates the untreated cluster periods. So that's just the treatment effect in this section. In the shaded boxes, we have the intervention effect that's assumed when we assume a constant treatment effect model. So we assume our constant treatment effect is theta, and for example, that the effect of 4 units or months of exposure time is the same as the effect of 1 unit or month of exposure time. So we only estimate 1 parameter for the treatment effect in this model. On the other hand, we have a general treatment effect model where we use a categorical term for each level of exposure time, which is kind of the most flexible model-based representation. And so here we have that the effect of 1 unit of exposure time is theta 1, the effect of 2 units is theta 2, the effect of 3 units is theta 3, and the effect of 4 units is theta 4. And so you can kind of see that by the nature of the design, the sample size is going to kind of decrease as exposure time increases. And so the variance of those estimators is going to kind of increase as exposure time increases, which we'll see more of that later. So to summarize these 2 models and kind of why we wanted to propose a new formulation, for the constant treatment effect model, kind of as Lee was saying, theta can be completely outside the range of exposure time effects when there are trends. The interpretation of theta is unclear in the presence of exposure time heterogeneity, and there's poor coverage when there are exposure time trends because the variance isn't accounting for the exposure time heterogeneity. On the other side, the general treatment effect model doesn't place any assumptions on the exposure time specific effects. It has performed well in simulation studies, but at the cost of wide confidence intervals because you are estimating, you are using up kind of your degrees of freedom on your exposure time specific effects. The information is not going to be pooled across exposure times. And as I mentioned, the standard errors are going to increase with increasing exposure time. So because of this, we propose a kind of random treatment effect model formulation where the effect of E units of exposure time is phi plus delta sub E, which we assume to be normally distributed with mean phi and variance sigma squared delta. And so this basically means that we've reduced the problem of estimating capital E parameters to estimating 2 parameters, the centrality parameter of the heterogeneity and the degree of heterogeneity, sigma squared delta. Here, outcomes are going to be conditional on a specific realization of random delta E. So in order to properly quantify the standard errors associated with the treatment effect estimates, we need to use bootstrap-based methods instead of standard model-based estimates. I can definitely go into more detail about this after, but yeah, this is a very high-level explanation. And if we were looking at our kind of diagram again, we still have a unique estimate for each level of unique level of exposure time. However, we now are only estimating 2 parameters, phi and sigma squared delta. And so we'll kind of explore this more in the discussion and simulation. It's also, we also would like to be able to test for exposure time trends. And so here are kind of existing methods, which are 2 natural possibilities for assessing exposure time trends. So we could just test if theta 1 equals theta 2 equals theta E in the general treatment effect model. You can use a score, likelihood ratio, or Wald test. Or you could also test if sigma squared delta is equal to 0 in the random treatment effect model that we just introduced. However, this places the null on the boundary of the parameter space. So it's complicated to derive the asymptotic null distribution. Even if you are able to derive that distribution, simulation studies have shown that in finite samples, this distribution still has low power. So we kind of wanted to come up with an alternative. So because of that, we propose a permutation test in order to test whether sigma squared delta is equal to 0 in the random treatment effect model. So the procedure is that you first compute the standard likelihood ratio test statistic in the observed sample, comparing sigma delta squared equals 0 to sigma squared delta greater than or equal to 0. And then among the treated observations, you randomly permute the exposure time indices within each cluster, and then you compute the likelihood ratio test statistic for that permutation. Of course, usually there's too many permutations to enumerate, so you would take a sample. Repeat this process capital B times, or B is like 1,000 or 2,000. And then you just calculate the p-value as the proportion of permutation samples with QB greater than or equal to Q observed. We also are interested in estimating certain parameters from these models, but in the presence of exposure time treatment effect heterogeneity, there's multiple parameters we may be interested in. So in all models, we can consider an exposure time specific effect or an average treatment effect defined here by the unweighted average of all exposure time specific effects. And so for each of the 3 models we've gone over, I have in the first row the definition of the average treatment effect, and then in the last E rows the definition for the exposure time specific treatment effect. So for example, for the constant treatment effect model, we estimate every parameter to just be theta. And then for the general treatment effect model, we just take the simple average of the exposure time specific treatment effects. And for the random treatment effect, since we're assuming delta is centered at 0, we just take the centrality parameter phi. So to motivate this work, we considered a tuberculosis trial, and I know I'm kind of going over time. So this trial had 14 laboratories and 8 steps. And so overall unfavorable outcomes, which was just a composite binary outcome defined by death, loss to follow-up, transfer out, or suspicion of drug resistant. And they found that unfavorable outcomes were not reduced in the intervention arm. And to illustrate our methods, we used the 3 testing procedures I mentioned to test for exposure time treatment heterogeneity. We didn't find any, so we updated the observed outcome values to make kind of a synthetic data set with an ordered normally distributed time treatment formulation. The plot didn't come out great on the screen, but we have exposure time on the x-axis, and the plot shows the exposure time specific treatment effects for the constant treatment effect model, the general treatment effect model, and the random treatment effect model. And the true odds ratio is kind of in the dotted line, and it's the same for each because it's the truth. And so for the constant treatment effect model, we see we have kind of narrower confidence intervals and just this constant treatment effect. For the general treatment effect model, we have increasing standard errors with exposure time, and the confidence interval is quite wide at the final exposure time period. And for the random treatment effect model, we kind of see a compromise. The effect estimates are mediated as well as the standard errors. We performed a 2 minutes, okay. So we performed a power simulation to calculate the empirical power for the 3 tests that I mentioned. So likelihood ratio test based on the general treatment effect, based on the random treatment effect, and then our proposed permutation test. And we varied the number of exposure time periods in each. So this plot shows the result. Sorry, I had my timer going. This plot shows the results of our power simulation. So the 4 panels are capital E, number of exposure time periods equals 3, 5, 7, and 9 respectively. And we have the 3 tests I mentioned. So in blue, the likelihood ratio test, testing those E parameters. In orange with the dotted line, the likelihood ratio test based on the random treatment effect model, and the solid yellow line is our permutation test. And something that we found, which others have mentioned at this conference, is that the likelihood ratio test actually had an inflated type 1 error rate when in actually all situations. So the type 1 error rate was over 5%. And then as consistent with previous research, the likelihood ratio test based on the random treatment effect model was conservative, and the permutation test was able to have high power while still retaining the desired type 1 error rate. Since I'm running low on time, I'll just go over quickly the results of our simulation studies for the estimation of the average treatment effect. And so we considered 4 simulation studies for plausible forms of exposure time treatment effect heterogeneity. So treatment effect constant, treatment effect normally distributed, treatment effects increasing linearly, and treatment effect delayed and then plateaus. And then we assessed how well the 3 models estimate this average treatment effect. So when the treatment effect is constant, all models are going to be correctly specified. And so all models are unbiased. One thing that we found was that the random treatment effect model had efficiency very similar to the constant treatment effect model, with the standard errors from the general treatment effect model substantially larger in the presence of exposure time heterogeneity. The general treatment effect model is always unbiased, and the constant treatment effect model was always severely biased, was severely biased in the case of exposure time treatment heterogeneity. And the estimators from the random treatment effect model have very similar performance to the general treatment effect model in terms of bias and efficiency, with the random treatment effect model being generally slightly more efficient than the general treatment effect model. I'm going to skip this slide. So just to conclude, our proposed model and permutation test offer a flexible alternative for assessing treatment effect heterogeneity in step wedge trials, particularly with a large number of time points. So if you know the form of treatment effect heterogeneity a priori, of course, a more parsimonious model would be appropriate, such as delayed or linear treatment effect, which I didn't mention here, but it's in the paper. If this information is unknown, the general treatment effect and random treatment effect models kind of present more robust alternatives. And as the number of exposure times increases, the random treatment effect model kind of becomes more and more efficient over the general treatment effect model when you're estimating the average treatment effect. And then I just want to acknowledge the PCORI grant and my collaborators and the study team. So thank you.
Thank you very much, Laura. Questions online? No questions online. I see some hands up here. Jess or Reese? I think Jess's was a fraction beforehand. Go ahead. Yes.
Thanks, Lara. Is this on? Yes. I think this is really interesting work. Thank you for that. And something I'm wondering about is, well, quite often when I work with trialists, they're really interested in extending the right-hand side of the stepped wedge design, so including more and more data collection periods when all of the clusters are implementing the intervention. And I'm curious whether this work has any implications for that, for how long we should be or could be extending this data collection period at the end of the trial. Any thoughts?
Right, that's really interesting. I mean, this work can still be applied in that case, like you would still, sorry. You would still be able to estimate the exposure time specific effects. And actually the general treatment effect model may work better in that case because you have more information in the later time periods than you would in the standard model. But we do have, the slide I skipped had like practical implications for trial planning. So we do have a formula we derived a formula for sample size based on the general treatment effect model. And so you'd be able to use that to kind of assess what the most efficient design would be.
I guess I'm wondering if there are any implications for maybe like the information content of those later periods as well, potentially, if you do have this heterogeneity going on. But that was
right.
Something I'll be thinking about.
Yeah, no, that's really interesting. Thank you.
Thank you.
Okay, yeah, hi, thanks. Yeah, very interesting.
Thank you.
So often you might think that a treatment effect just takes a while to ramp up and then sort of tapers off or something. And so there'd be some sort of constraint on the exposure time treatment effect graph it's just non-decreasing or something. And I guess what you might be interested in the bits at the far end. And as you say, there's not very much information on those in the step wedge design. But is there a way to sort of incorporate that non-decreasing nature in the estimation itself?
Yeah, so I actually only presented the case where the random effects are normally distributed. You could put any distribution on those random effects. You could put a uniform distribution, and you could put, I mean, if you're willing to use more like Monte Carlo based methods for estimation, you could, I think, put any constraints you wanted on the random effects. And that's a great question.
Okay, thank you. Yeah. Thanks very much.
Just one. Was there another question? Oh, yes, please.
So I think you had assumed exchangeability within clusters in the work you presented. Is that right?
Yeah,
just a random effect cluster. Have you thought at all about whether you could relax that assumption with random effects for time or different correlation structure within clusters?
Yeah, that's definitely that definitely would be interesting. We basically kept it as simple as possible because in our case we now have a crossed random effect, which is not really available in much software. But yeah, I think that would be an interesting kind of next step to relax that assumption.
And I'm also very interested in how you did the bootstraps. Maybe I'll ask that.
Yeah, for sure. Thanks.
Just one final point, I guess, from me. It seems, and certainly from your examples, your approach with a random effect is like a shrinkage version from the separate parameter at each time point. So you probably could, probably analytically not possible, but to be able to see your parameter estimates as a weighted combination of the common intervention effect and then the specific intervention effect, just like any sort of random effects type analysis. I mean, that might be just something to
I think
to think about, or I don't know what stage your paper's in, but it'd be a nice sort of explanation about it, because your examples showed the common intervention effect and then these hugely variable things, and then yours were like a shrunken version of those.
I think under like continuous outcomes and with some simplifying assumptions, I could definitely do that. So thank you.
Yeah.
Oh, but also I wanted to plug the paper. It's going to be published in Biometrics Practice. So.
Oh, fantastic. Excellent. Okay, so thank you very much. Okay, final talk for today by Jules Pereira Macedo. I probably brutalized your name, my apologies. From University of Tours, who's going to be talking about estimation of a risk difference in cluster randomized trials. Okay, thanks very much.
So, hi everybody again. I'm Jules Pereira, a PhD student from the University of Tours. and I will talk about my work on the estimation of a risk difference in a cluster randomized trial. So when we talk about risk difference, is doing a difference between the proportions when we have a binary outcome. And as we know, for the randomized control trial and cluster randomized trial, the consult recommendations are to report both relative and absolute treatment effect by estimating the odds ratio and relative risk for the relative effect and the risk difference for the absolute effect. And despite these recommendations, as shown in the work of Turner and Hall, most of the time we only report the relative treatment effect, because maybe when we have a binary outcome, we have to do logistic regressions and we estimate directly the log odds ratios. So reporting only the relative treatment effect. So Pedrosa and Trong works on a simulation study evaluating difference method to estimate a risk difference in the multi-center trial. So their limits of this work is that a multi-center individually randomized trial, and they have only one individual covariates and no confounding factors in their data. So this motivates our work, was the objective to compare by a simulation study methods to estimate the risk difference in a cluster randomized trial with confusion factors. So our simulation plan will be in 3 steps. The first one will be to generate an outcome, will be correlated between individuals in the same cluster with the intra-cluster correlation coefficients. Then we will generate covariates, will be correlated with this outcome, and we'll make coefficient factors with these covariates. So the first step, we will generate our outcome YIGL following a binomial distribution with the parameter pi with the prevalence of the high harm. YIGL will be the outcome of the L individual of the G cluster of the high harm. Will be a combination of 3 random variables with binomial distributions, and 2 individuals of this within the same cluster will be correlated with the value rho ICC with the intra-cluster correlation coefficients. Then we have simulated our outcome. We'll simulate our covariates. Xig of M is the mth covariates of the outcome YIGL, following a binomial distributions with the parameter QM, the prevalence of the mth covariate. So XIGLM is a product of 2 random variables following binomial distributions. And the correlation with the outcome YIGL is equal to rho M, the mth correlation between the covariates and the outcome. So we simulate these covariates in the same way for the intervention groups and the control group. So now with this covariate, we'll include confusions in our data. So the main idea is to simulate a random variable ZIGL will be equal to 1 if we include the individual in the trial and 0 if not. This random variable will follow binomial distributions with the parameter EIGL with the probability to be included in the trial or not. And this probability depends on the covariate XIGLM and the betas will be fixed by us depending on the covariates and the arm of the individual. So now we have generated our data. we'll use a marginal approach to calculate our risk difference using the generalized estimating equations. So we'll have three different methods. The first one with the Gaussian distributions, the second one with the Poisson distributions, and the third with the binomial distributions. So for the first one with the Gaussian distributions, we'll use a limb function identity with an exchangeable correlations matrix. And we will directly with the GE estimate our risk difference by estimating the coefficients beta 0. And then for the two other methods with the Poisson and binomial distributions, we will use the G computations to estimate our risk difference with each their link functions, logs and logit, and still with an exchangeable correlation matrix. So the G computations will be in four steps. The first one will be to do the regression to estimate our parameters beta and alpha. Then the second step will be to duplicate our sample. So in this example, the blue group is the intervention group, and in orange, the control group, individuals. So we'll take the intervention individuals, we'll duplicate their data. So we will have 2 times the same outcome with the same covariates. And then we will create a counterfactual events on the harm allocations. And we will do the same for the control group, duplicate them and create a counterfactual on their events. And then we will estimate the probability, success probability for each individuals with the regressions did in the first step. And then we'll calculate this risk difference by doing the difference between the success probability of the individuals and the counterfactual events. So for our simulation study, we have 81 scenarios with the parameter number of cluster harm, 3 variables of ICC, 3 pairs of prevalence with P1, the prevalence of the intervention harm, and P0, the prevalence of the control harm, and 3 variables of number of covariates, 0, 1, and 3. So I will present you my preliminary results, starting with the bias, and ICC equal to 0.001. So 2 columns representing the 2 pairs of prevalence, 0.1, 0.05, and 0.5, 0.4. 3 rows corresponding to the number of covariates, 0, 1, and 3 covariates in our data. The x-axis representing the number of cluster per harm, and in y-axis, the bias. So we have our 3 methods. In red, the binomial logit, in green, the Gaussian identity one, and in blue, the Poisson log one. So we can see, despite the fact that when we have 3 covariates in our data, we see a little difference between the bias of the Poisson log methods with the 2 other methods, but remains a low bias for each scenario near 0. Then we'll present you the coverage rate. So for the coverage rate, we see that for a small number of clusters, we have a low coverage rate and far from the nominal value of 95%. And when the number of cluster per harm increases, then the coverage rate increases too. And we have no difference between the methods. Then we wanted to see the empirical standard error. So we see for all the scenarios This is the Gaussian identity method that minimizes this value. And then in summary, it's what I said in the 3 previous slides, and I will add that for the other scenarios, so for the 2 other value of ICC and the 3rd pairs of prevalence, the results are similar. So in conclusions, the G with Gaussian distributions has the lowest empirical standard errors and is the easiest to implement. And this perspective of this work is to add a small number of cluster correction to improve our coverage rate and to introduce cluster level covariates. Thank you.
Thanks very much, Jules. It's great to see a conclusion of you can do something simple that works rather than you have to do something more complex. I know it's very close to lunchtime. Questions online? Any quick questions from inside here? Just a quick comment. I know with unclustered data, they've also shown the just analyze a linear model works quite well too. So it's good to see that it works in the cluster randomized setting too. Yeah, and I suppose you could put in small sample corrections to the robust variance to maybe make it a bit better with smaller number of clusters too. But still, no, that's good to see a nice simple solution. Okay, so thanks very much, Jules, and thanks to all the speakers from this session. And a wonderful lunch is awaiting downstairs, upstairs. Up the stairs, yes.